Hi. So previously we discussed a very famous reinforcement learning algorithm called DQN, but that's only available to study if there is only one single agent as the individual who is making the decisions in the dynamic environment. So would it be possible to have some algorithms in reinforcement learning to model the interactions between multiple agents, okay, if they're trying to coordinate to solve some task together, okay? And there are many kinds of algorithms in RL addressing this kind of problem with multi-agent reinforcement learning, okay? Sometimes we call this MARL, okay? Um, so there are many different aspects of this research in this kind of problem. And among those approaches, one concentrates on the communications between those agents when those agents are trying to solve some problem together. Okay, so today we'll introduce this paper and together to have a look on this paper to see how the authors in this paper they try to model this situation to let the agents, multiple agents, to learn to how to communicate and to discover or explore some meaningful or useful communication protocols for those agents to be able to communicate. Okay, when they're facing some problem. Okay, so now we go into this paper. So this paper is called "Learning to Communicate with Deep Multi-Agent Reinforcement Learning." Okay, and as we mentioned, there are also some other kinds of papers regarding the multi-agent reinforcement learning, but different papers they might focus on different aspects on the multi-agent reinforcement learning. Okay, so this one simply concentrates on this learning of the communication protocols of the multi-agent RL problem. Okay, good. So let's have a look on the abstract of the paper. So they consider this problem of the multiple agents sensing and acting in environments with the goal of maximizing their shared utility. Okay, so in environments, agents they must learn communication protocols. So normally, when we try to model the communications between multiple agents, so using either like game theory approaches or any other approaches. So normally we have already given those such communication protocols in advance, right? So agents they just need to follow the protocols and then communicate to each other. So this paper is very different that they provided this approach that they allow the agents to discover some communication protocols, okay, in during the learning process. Okay, so in order to share the information that's needed to solve the task. Okay, so embracing the deep neural networks. So essentially, this model will use the DQN as we mentioned last time. Okay, so DQN is a very important part in reinforcement learning. Okay, and this is end-to-end learning of protocols in complex environments, inspired by communication riddles. So in this paper, they discussed two different kinds of games. One is so-called communication riddles with some prisoners, and they try to communicate with some protocols and using some light bulb. And they also discussed another game called Amnist digit number game. Okay, we will later introduce those two different games. Those are just examples, and the arenas or the games for the agents to explore. Okay, so and those are both some games or some problems with partial observability, and of course those are dynamic scenarios. So they this paper basically proposed two different approaches. Okay, so one is called RIAL or reinforced interagent learning, and another one is called DIAL, which is differentiable interagent learning. Okay, and they compared those two different algorithms, and the DIAL, the latter one, is much better than the previous one. And the underlying reason of that is because DIAL captures some gradients by the messages directly between those agents. Okay, and we'll see the figure later to why that the DIAL is always better than RIAL. Okay, so and they said the former the RIAL uses deep Q-learning, and the latter explores the fact that, as we just mentioned, during learning, agents can backpropagate error derivatives, so which are just the gradients, through some noisy communication channels. Okay, so they simply communicate through those messages directly and use those messages to update their gradients, and they don't need to actually to retrieve those gradients from the environment, right? Uh, Based on the original DQ. Okay, so and it also uses centralized learning and decentralized execution. Okay, so it means that in centralized learning, they share all those parameters, and they have a richer space, or they have a more general setting of the communications. And but during the decentralized execution, so they some of the resources, or there are some constraints on those. Okay, and later we'll see what's the difference between those two. Okay, so and they also said the experiments introduce some environments. So those are different kinds of games for studying the learning of communication protocols, and present a set of engineering innovations essential for success in those domains. Okay, good. All right, so now let's skip the some stories, backgrounds, and let's go directly into the mathematical parts. Okay, let's have a brief review on the DQN and some other things that they will base on for this paper. Okay, so in DQN, it's a single agent, fully observable RL setting. Okay, an agent observe current state S at time step T, and action is denoted using U. Okay, according to a potentially stochastic policy pi, and we have already discussed this DQN before, right? So this will be a very brief review. Observer will signal RT and transits to a new state S plus one. Okay. So the objective is to for a single agent is to maximize an expectation over the discounted future return. Okay, and the RT will be the reward for time t, and gamma is discount factor. So the Q function of policy pi would be just the expectation of all those rewards given S and U. Okay, and optimal action value function Q star would be just the maximum by choosing some pi to maximize this Q pi. Okay, and that satisfies the Bellman equation, and simply we just expand those on these the current reward R and the future discounted rewards by using just one step ahead, right? S prime and U prime, and by selecting some U prime, this will maximize the discounted future rewards Q star. Okay, so and using the neural networks, it's not hard to find out by simply inputting all those U primes, and we will find try to do the best prediction as we can for this Q star, for the maximum Q star. So deep Q learning using neural networks parameterized by theta to represent this Q. Okay, and DQ is optimized by minimizing the loss. Okay, so this loss would be the expectation of this experience replay, and this would be the square distance between the label or the target with this Q value. Okay, so this target, as we mentioned, will be the R plus the discounted future maximum future rewards. So this will be the best prediction that the agent could make given that there's some experience replay, right? So the agent already know that the next state S prime, and by choosing some U prime for the next state, and this will maximize the discounted future reward. So here, this theta I minus, this will be simply the same, exactly the same network as data, but here we freeze that for a number of iterations, or update the online network for the stability. Okay, so action U is chosen from this queue by some action selector, and simply use this epsilon greedy policy. Okay, good. So this would be the importance of experience replay, and that would be important in TQM, since only if we have this experience, which is the tuple of S, U, R, and S prime, so that the agent will be able to use this experience to try to make the intertemporal prediction as best as this agent could, right? To have to obtain the gradients to update the Q function, or to update the network, right? Okay, so good. So that would be a TQN, and here the authors, they also mentioned some other things based on TQN. Okay, some other algorithms. So and we could observe that those independent TQN or deep recurrent Q networks are the basic components or the basic algorithms that the authors in the paper, they will build their algorithms on. Okay, so independent TQN, let's have a brief look. So TQN has extended to cooperative multi-agent settings where this agent A, so they leave A as the agent and U is the action. Okay, observe the global state, select individual action, and receive a team reward. Okay, shared among all the agents. So some address the setting with a framework that combines DQN and independent Q learning. Okay, so we can see that a lot of works in the reinforcement learning, or even in many fields, they just combine different studies, right, and to provide with some new approach, in which each agent A independently and simultaneously learns its own Q function. Okay, independently and simultaneously. This is important. While independent Q learning can, in principle, lead to convergent problems. Okay, so this is very obvious, because if some agents learning something, then this will make the environment changing, right? So this environment is it looks like some non-stationary problem to other agents. Okay, good. So, and here they also introduced a recurrent network. Okay, so since both DQN and independent QN, they assume some fully observability, but and it's obvious that in most of the cases in real world scenarios, we don't have full observability. So instead, we often have a partial observability. Okay, so here S is the hidden state, an agent they could only observe some observation OT, and which is correlated with ST. So some people, they propose this deep recurrent Q networks to address this single agent partial observable settings. Okay, and instead of approximating Q with the feed-forward network, so instead they approximate Q of O and U, which is, instead of having S, they have this O as the partial observation with the recurrent neural network that can maintain an internal state. Okay, so maintain internal state and aggregate observations over time. Okay, so this can be modeled by adding an extra input. So this is very similar to RNN, right? Recurrent neural networks. But just they implement this recurrent networks into the DQN, right? And represent the hidden state of the network, yielding Q, OT, HT minus 1, and U. And okay, good. So those would be the tools or the basic parts that this paper build their algorithms on. So now we could jump into their model and have a look on their setting. Okay, good. So they addressed that this would be a problem with multiple agents, okay, and some partial observability. And it would be easy to consider there are only two agents, okay, and they did in their examples. So odd agents, these are the goal of maximizing some same, discounting some of real words, while no agent can observe the underlying state, Markov state, and each observe partial observation correlated to that. And in each time step, the agent selects an environment action U, okay, that will affect the environment. And also there are some other action called communication action M, so which is a message. And this message can be observed by other agents, okay? But this message doesn't have any impact on the environment or reward. And this is very similar to some settings, classical settings in chip talk or Bayesian persuasion, if you're familiar with some game theoretical models, okay? Good. So, and we are interested in such settings because on any multiple agents, parts of observability coexist, the agents have the incentive to communicate, okay? Good. So as no communication protocol is given in advance, the agents, they must develop and agree upon some communication protocols to solve the task. So this would be the key sentence of the whole paper, right? Good. So, all right. So now let's move on. And since protocols are mapping from the action observation histories to sequence of messages, so the space of protocols is a high dimensional. Okay, so automatically discovering effective protocols in a space, this is a challenge. Okay, and yes, of course, and in particular, the difficulty of exploring the space protocols exacerbated by the need for agents who coordinate the sending and interpreting messages. Okay, so here they give example. Let's say if one agent sends some useful message to another agent, it will only receive positive word if the receiving agent correctly interprets and acts upon that message. Okay, if it doesn't, the sender will be discouraged from sending the message again. So the difficulty is that the positive rewards are sparse. Right? So this is a very common problem in reinforcement learning, arising only when sending and interpreting are properly coordinated. Okay, so here they explained what is the centralized learning and decentralized execution. So this is a very common thing in reinforcement learning problems. So they said this means that communication between agents is not restricted during learning, so they could fully communicate in a continuous channel, right? So which is performed by a centralized algorithm. However, during the execution, after the learning, agents, they can only communicate via some limited bandwidth channel, which would be discrete. Okay, so not all real world problems can be solved in this way, and some they could. So, for example, when training a group of robots, some simulator and decentralized planning and decentralized execution. So this is a very standard paradigm for this multi-agent reinforcement learning problem. Okay, good. All right, so now we move on to the experimental design, or before that, we need to introduce the architecture of the model. Okay, so this would be the highlight of the whole paper, right? So here, let's go directly into those figures. Okay, so those two figures, they introduced the two algorithms that they discuss in this paper. The first one is RIAL. It's reinforced based communication. Okay, and the second one is DIAL. Is differentiable based. So the difference is that, so here, how do we understand this picture? Okay, so there are two agents. Okay, so agent 1, agent 2. So let's focus on the picture on the left first. Okay, so Perhaps let's use this orange. Okay, good. So here they simply show only the messages from agent 1 to agent 2, okay, from period t to t plus 1. But they just omitted the message from agent 2 to agent 1 from t to t plus 1, okay, for simplicity of the picture. Otherwise, it will be very confusing, okay. So we can see that the message from agent 2 from period t minus 1 goes to the QNAT at time period t, okay. And what else is that the agent 1 also observes some partial observation from the environment, right? And those two their input into the QNAT, and then the action selector outputs two things. Okay, so the first thing is this message from agent 1. Okay, so it's symmetric for agent 2, but here we simply talk about one stream of that, okay, for simplicity, as we just mentioned. Another action that the action selector outputs will be this actual payoff relevant action, okay. So as we can see, this payoff relevant action UT, of course, it goes to the environment and affects the environment, right, and affects the next state. But this message, it goes to the other agent, okay, goes to the QNAT for the next period, okay, and then this simply that'll be the whole loop, right, and the next t plus 1, so in next stage it'll be the same as before, okay, and this those red arrows, they are simply the gradients, okay, so so this gradient would be useful for update the for the DQN, right, to update the parameters theta for this deep Q network learning, right? Okay, so that'll be RIAL. Okay, so something even more sophisticated, even better, is this dial on the right. Okay, so let's first reduce all those. So now let's use orange first. So the input, okay. So the input for okay, for let's see, for the agent 1 here, of course, we have this observation from the environment, okay, and there are also some message, right? So this would be, so they forgot to put some label here. So this would be m t minus 1 from player 2, right? mt minus 1, 2. Okay, so this would be also an input to, I think they call this as CNAT. Okay, so this is just another version of QNAT. We'll introduce that later, but it's just some networks. So the inputs are OT1 and MT minus 1, 2. Okay, so the message from the other player from the last period and the partial observation from this period. So the output, okay, so the only thing that action selector outputs is this payoff relevant state, payoff relevant action, okay, UT1, and that goes to the environment that affected the next state. So the message, we can see that here the message, it doesn't come from action selector as before, right? So here this message comes from the CNAT itself, and it directly after goes into this DRU, this unit, and then it directly goes to the CNAT for the other agent in the next period, okay? And the T plus 1 period will be similar as before. Okay, so this will be this, and we also have this gradients. Okay, so the gradients from the environment goes back to the action selector and goes back to CNAT, and there'll be another gradient, very importantly, from the other agent CNAT and goes back to DRU, this unit, and goes back to CNAT for the message gradient. Okay, so there will be two different gradients. Okay, two flows. Good. So we can see that those two are completely different settings, right? So in the dial on the right, they have some extra flow or extra flow of the gradients for the messages, right? So, and this is actually very helpful to help this dial algorithm to achieve a much better result than RIAL. Okay, good. So those are, I think this will be very useful for us to understand the basic. Let's go back to the highlight. Okay, so this will be a useful explanation for us to understand those two different architectures. Okay, good. So let's see what else important for us to capture here in this section. So for RIAL, as we mentioned, so they have each agent's Q network is this, right? So as we mentioned, so the message from the other player and OT and this H, as we mentioned, so this H will be something from the in the hidden state, right, in the recurrent network. Okay, right, and something very important, okay, is that this message, okay, so this M. So what do we mean if when we are trying to model or try to let the agents to explore or discover some communication protocols? So in this paper, very interestingly, they model this communication protocol as simply as some message, which are also the input and output of the CNET or QNet. Okay, so using this deep learning, this idea of the deep learning, so they simply put this message or this M as some input and outputs for this network. Okay, and that'll be a very interesting and unique approach to model how agents they communicate, right? Okay, so this would be the key. The key contribution or the key insight of this paper, right? Of how to model this communication of different reinforcement learning agents. Okay, good. So here the authors also mentioned this parameter sharing, right? So, and those are just some technical details with parameter sharing, and later we will see that in the results, the results will be much better than the case without any parameter sharing. Okay. All right. So good. So that's RIAL. Okay. And how about DIAL? So this would be very similar. And the difference is that they, as we mentioned, they have two different gradient flows. One for the DQ as before, and another one is for the message gradient. Okay, and here another difference is that they have the CNET. Okay, and which is different from that QNet as before. Okay. All right. Good. So, and they also introduce this discretized or regularized unit DRU. Okay, so this will be useful to introduce some noise into the learning. Okay, and this will be also useful to understand the difference between the centralized learning and decentralized execution. Okay, and here they already said that, right? So DRU regularizes this during the centralized learning with that logistic function, and it discretizes as using decentralized execution. Okay, and this will be different than before. Okay, and the sigma will be the standard deviation of some Gaussian noise added to the channel. Okay, good. So the remaining will be just some small details that you if you are interested in this paper, then you could have a further look on those. Okay. All right. So next part will be the experimental design and results. So before the examples, they introduced the model architecture, so which gives some introduction on the hidden state architecture, right? So here we can see from this picture directly is that in each time step, we have what we have the input for this Z. So this Z will be okay. Let's see what is this, right? So each agent consists of recurrent neural network unrolled for T time steps and hidden state H, an input network producing an embedding Z, and output for the Q value and message M. Okay, so basically they're at each time step there are two different. The last one doesn't have message, right? So previously all those other periods they have two outputs. One is Q value, another one is message value. Okay, so and also the message is input for this network. Okay, so the input for agent A is defined as this. We know this before, and A and U T minus 1A they are passed through some lookup tables, and the message from T minus 1 from the other agent through a one layer MLP and producing a size of 128. And this observation is processed through some network that produces additional embedding of the same size. The state embedding is produced by element-wise summation. Okay, so this Z will be just the element summation of the MLP of OT and the MLP of MT minus 1 and the lookup table for UT minus 1A and for this A. So this A will be simply some index, right, for this agent. Okay, so and they said they also use a batch norm and for T minus 1, and this ZTA is processed with the two-layer RNN, so they have two layers of those hidden states right here. Okay, so it's okay. So both are using some GRU units. Okay, both layers. Okay, and those RNNs are useful to approximate the agent's action observation history, right? Because those they're trying to capture the real state, but the real state is not observable, right? So they could only use the OT, use the partial observation to infer about the true states using this structure, neural network, recurrent network structure. Okay, so the output is output, which is the those outputs right on the top here of those H's. Then pass through a two-layer MLP. Then the output, final output, will be the QT and MT for agent A. Okay, good. So this is the structure of the recurrent models. Okay, so next, before the results, we need to introduce the experiments. Okay, so they provided two different games. So the first one is this prisoner information game. Okay, so this basically this game is saying that okay, here they have the introduction. So 100 prisoners they're into the prison, and the warden gives them a game that starting tomorrow, each of them they will be put it into some cell. Okay, and they cannot communicate to each other. Okay, and each day the warden could choose one of those randomly and uniformly. Okay, so and and in this little room there's only one light bulb. Okay, with a toggle switch. So each person they could observe the current state. Okay, and if this person wishes, then could change or toggle this light bulb. Okay, so each person also has the option to say that all visitors have visited this room. Okay, and this would be the tile, this action. Okay, so if the announcement is true, then they're all good with a very high reward. But if false, then all prisoners are dead. Okay, so it's very bad, right? So very low reward, even negative. So then the warden allow them to discuss together, and they want to ask that can they have some protocol to let them to have a high reward. Okay, good. So this is a very interesting game, and we wonder that how should those people communicate and try to work out some such communication protocols, right? And it's also very interesting for us to wonder that if whether really those algorithms, reinforcement learning algorithms, are helpful for discover those communication protocols, right? And later we will see the results. Okay, so now let's have a further look on the architecture. And each agent observe this O, okay, and the switch has two positions. That'll be a 1-bit message. If agent A is in the room, then the action will be not do nothing or tell. Okay, otherwise the action is nothing. Okay, the episode ends if this at tell, or the maximum step is reached. The reward is 0 unless if someone says tell, and it's 1 if all have been to the room, and -1 they're all dead. Okay, so and this says the maximum time step would be some linear function of this number of agents. Okay, and this experiments m t minus 1a will be available only to agent A in the room. Okay, good. So here in this picture we can see the results of this experiment, right? So if there are three people in this game, and we can see that the maximum reward the algorithms could obtain will be 1. Okay, so that will be the best. And here we can see that the RIAL in green achieves the best outcome, and here the blue in RIAL, it also later, after about 1.8 or 2k epochs, the RIAL in blue also reaches the best reward with 1. But if we can see that if there are no parameter sharing either in RIAL or dial, if it's dial, even if there's no parameter sharing, then the green dashed line still could reach 1. But for RIAL, it cannot reach 1. Okay, it's about 0.98 to 0.97 something. Okay, and the orange one is there's no communication. Will be the baseline. Okay, so and this will be the result for 4 players, and this will be even more complicated version of that. And you can see that again, dial outperforms the RIAL, and the parameter sharing outperforms the case without any parameter sharing, right? Okay, and this little figure is very interesting, and it visualizes the result that the best communication protocol that agents they could achieve, right? So basically, this is very interesting the way that in day 1, okay, so this is the sort of the optimal strategy. Okay, so in day 1, if this person goes to the room, then this person simply switch that light bulb on. Okay, and in day 2, and if an agent comes to this room, and it will ask this agent itself then if this agent has been there before. Okay, so if yes, if the agent has been there before, then simply switch it off. If the agent doesn't come to that room before, then keep this on as before. Okay, and on day 3, and this person asks themselves that if this agent come to the room before, if yes, if this agent came to the room before, and this person does nothing. Okay, if this person doesn't come to this room before, okay, and if the switch is on, then this person need to tell that everyone has been to this room before. But if the switch is off, then this person switch this to be on. Okay, and this is day 3 plus, and more to go, right? If the game doesn't end. Okay, and you could use several minutes to verify that this is actually the optimal strategy that the players they could have. Okay, and this the basic intuition behind this solution of this game is that they try to use the light bulb or this sort of the intertemporal space to help them to actually to communicate whether everyone has been there before. Okay, and if you have time, you could have a little bit further thoughts or thinking on this little problem, and it would be very interesting to further consider that. Okay, so okay, we don't have too much time to further explore on the theoretical part of this example, but here this model simply shows a very strong prediction or strong ability in the solving this kind of problem and allow the agent to try to communicate for themselves and to work out this communication protocol together. Okay, good. So so this would be the first example that they have in this paper. So the second example is called amnist games. Okay, so in this game there are two agents, and each of them they are given some there are two different kinds of games, right? So on the left, so each of the player they are given if an agent they're given some grayscale number, okay, from 0 to 9, and they're in total they're set they can only have five time steps. Okay, so after 5 time steps they have to guess what is the correct number, and the reward will be given finally. Okay, so they this will be simply just some game to test the ability of this algorithm to map from the higher dimension, which is there are 10 different digits, right? So need to map that information, and this will be a picture with some pixels, right? So they want to test this ability of the algorithm to help the agents to try to map those information from a higher dimension with those pixels to some lower dimension with only 1 bit communication channel, right? And there are 5 steps allowed. So we can imagine that later what the agents they need to try to form, because they can only send 0 or 1 at each time step, right? And they can do this 5 times. So they need to use the orders or the 0 1s, like the 1 bit information with 5 times. They use all those opportunities to try to communicate the information that they get from a very high dimension of 2 times 28 times 28, right? So so this would be if there's no color, then there's no red or green, so there will be only 28 times 28, right? Those kind of those many of pixels. Okay, so how do they map from the so this model simply captures how do they map from this high dimension of pixels of a number or a digit to this low dimension of 1 bit messages with 5 time steps. Okay, and the other game will be similar to that, but this will be just the color. Okay, all right, good. So again, in the results we could see that again a dial outperforms the RIAL and compared to the baseline with no communication, and parameter sharing, of course, again is better than the case without parameter sharing. And here with the color digit, and they have the similar results. And here the protocol of this game, amnist game, will be as we mentioned before. So there are four chances in total they can communicate, right? So in the last stage they cannot send any messages. So there are 4 chances they could communicate, send messages, and if there are different digits from 0 to 9, so at each time step they send different messages to the other agent, right? So we can see that they have already successfully encoded all those 10 digits into the 1-bit information, but with 4 time step. Okay, good. So this is those two are very well designed experiment, and they show a very nice property or the power of this algorithm to help the agents to discover or to explore the communication protocols in the emergent communications. Okay, good. So and later this paper also introduced some other theoretical results with the noise and the central learning and and execution. And also they introduced some details on those networks and algorithms, as well as the examples. Okay, good. So that'll be the basic or the main introduction to this paper, and hope this will be useful for us to have a further taste or a look on those very interesting reinforcement learning algorithms. Okay, and in this paper we could observe that if the agents they do not have any communication protocols defined previously, then using those kind of algorithms, they to input some messages and output those messages given some neural networks and based on the reinforcement learning. So the agents they are able to discover those communication protocols as we just see here, right? So those in this example or in the previous example, right? Okay, good. So later, if we have time, we could have a look on the code of this paper and try to introduce some other interesting algorithms.